started this exercise of writing the equation from the graph. And in that, we particularly want to note if there has been any kind of shift, vertical or horizontal, and if there has been a stretching. Vertical stretching, which is equivalent to horizontal shrinking, okay, and vice versa. And we did these exercises, the absolute value function, a straight line, a parabola, which has been inverted, by the way. One more operation that can happen is reflection, right, which has been reflected on the x-axis. And then we did inverted absolute value function, and the last problem we saw was the cube function, okay, which was reflected and then shifted up. We have two more to go here, and as you see the graph, you can understand that what is the parent function, and look at the shifts and see if anything has been stretched. Okay, let us start, right? You write the equations as always on your own and then watch me in the video so you can test yourself. The parent function in this case would start at the origin and go up like that, which you would call parent graph is y equals, sorry, not square, the opposite of that, right? Under root, square root of x, right? Now compared to that, my graph is at, that is at 0, 0, the, the leftmost point. The leftmost point here is -3, -1. So you can see here the shifts. 3 units left, 1 unit down. Right? And because of that, the new equation would be y equals 3 units left. So that adds to the input and 1 unit down. Okay. Now the only thing that remains to determine is if there is any kind of stretching, right? Now, based on my previous discussions, there are two ways of doing it. Method 1, method 2, I call them like that. And I can easily see through the visual inspection, which I called method 2, that there is no stretching applied here. Because this is 1 unit, that's 1 unit, which is also the same if you look at the parent graph. 1 unit, 1 unit, right? So it doesn't look like the graph has been stretched, but you can always verify. And that is also we had discussed. Use method 2 for a precise, computationally verified answer. Okay. So how would I determine computationally? Suppose it has been stretched. If it was stretched, vertically, let, you can say let y equals k times under root x plus 3 minus 1 be the actual, equation. Okay. Be the equation of the graph. Okay. Now take a test point and plug in. Plug in any one of the points. Okay. Let me choose Now I'm using method 2. I'm going to erase that and show here. This point is minus 2 comma 0, right? And we learned actually when we are doing the absolute value function or one of the other parabolas that don't choose the end point or some very standard point. Okay, like in this case, I think it may work, but I would prefer not to choose the minus 3 minus 1. Okay, I'll choose some other point, not the starting point. If you plug in minus 3 here, I don't know, it will become 0 minus 3 plus 3, and then you will not get the value of k. The goal of choosing a point is you plug in that point and find the value of k. Okay, so choose a point somewhere randomly in the middle of the graph. Plug in any one point. Okay, I'm also writing it here, so you can see it and realize the general process. Say minus 2 0, right, in this case. Okay, now if you plug in minus 2 comma 0 in this case, I'm going to continue on the left side here to leave space for the other problem. If you plug in that, it will be y is 0 here equals k times under root x is minus 2 plus 3 minus 1. Because there is no stretching, I'm expecting to get the value of k to be equal to 1. Okay, I bring the minus 1 from the right to the left, it will become plus 1 equals k times under root minus 2 plus 3 is 1, right, under root 1. So you can see very clearly you get 1 equal to k, which proves that there is no stretching or scaling from the original graph. Okay, let us do that for one more graph. Again, pause the video, write your equation, and then follow me here. Okay. Right out of the right out of the bat, I'm going to say there is no scaling again here. Okay, so let me get rid of that right away. You can see it's 1 unit, 1 unit. So I only have to think about the shifts and possibly some other action. We will see that. Okay. Now, if you think of the original equation, okay, your original equation was this graph, right? Y equals root x. This is the parent. Now, okay, number one, I can say it has been shifted, but even before I shift it, and this is my experience, okay, it's usually better. You can do the operations in any sequence. In all this time, if you have been thinking about how do I go about thinking? Do I think of the shift first? Do I think of the left shift or right shift first? Or do I think of any other stretching or reflecting first and then do the shifts? It should not matter. Okay. In theory, it should not matter whichever operation you choose to do first. What matters is how you write the equations carefully. Okay. And to me, it looks like taking care of the reflection if there is one first makes life easier. Okay. And I can see that the graph has been reflected here, right? The parent is facing towards right, but the graph that you have is facing towards left. So what you would rather do is look at its reflection first. Clearing this reflection, right? And let's write one by one. Okay, the pink graph here has been reflected. Now what reflection? That's a reflection on y-axis. If you reflect on y-axis, the plus x, the x coordinate becomes the negative x coordinate and vice versa, right? The y values, the vertical values do not change. The x becomes minus x. So the equation is of the violet graph there is y equals minus root x. Sorry, root minus x. Okay. Now think of the shifts. The black graph has been shifted, and you can clearly see that's I've done so many times by this time, the coordinate of the tipping point tip here will tell you how much it has been shifted, 4 minus 1. So that equation would be 4 units right. So under root minus x minus 4 because of the right shift. You are shifting the violet graph, not the red, not the original. Okay. And minus 1 because it's 1 unit down. All right. Okay. Let's move on. Absolute value function, graphs, equations, inequalities, and application. Okay. The next subsection is absolute value functions. We have seen the definition of the original, like the standard, the typical absolute value function before this, and we have looked at the V-shaped graph and all of that. Okay. We are not studying just that now. We are generalizing that concept. I mean, okay, for your quick recollection, the definition of absolute value function, right? We said, it also has a piecewise definition. It is x for x greater than or equal to 0 and negative x for x less than 0, because if it is already negative, if x is already negative, you want to make the negative of the negative and make it positive, right? So minus x for x less than 0. Now you want to take that and apply to a general function, absolute value of a function f of x. So what is happening here is two layers, two steps. Okay, there is already a function f of x. So the input x is given to the function f. It produces the output f of x. And you take that output absolute and get its absolute value and obtain its absolute value. Okay. That is f of x minus f of x here. Fine. How does that affect the graph? See, now when we apply this absolute value function, or when you looked at the original definition, we actually took the graph of the line y equal to x, right? That's the line y equal to x. And then we applied the concept absolute value. So on the right side of origin, on the positive x-axis, it remained the same. On the negative x-axis, it got reflected because the values of the y were negative and we took minus of that. So it became positive, and this was your result, right? The absolute value. Okay. We will do the same thing now to a general function, right? Let us look at some examples. In each case, we want to obtain, like first we want to sketch the graph of absolute value function, absolute value of the given function, and then write its domain and range. Okay. Now, you would be seeing it, but I'm going to reinforce it here. This is the given original graph. Okay. For its absolute value, from the left, I can see the values are negative, right? So you make it positive with the same magnitude, right? If you are now to do it precisely, what you should do is you should take some specific points and draw their counterpoints. Here -6, -3, the absolute value would be -6, 3, right? Positive value, and so on. Okay, you can check that. Whatever it is, -1 point something here. Yeah. Okay, so I did not do it correctly. That should go to 1 point something. Okay, and the -2 here should go to my 2 there. And let me try to sketch now more accurately, like that. A little higher seems to be better. I'm just trying to make sure that my graph looks as close to as possible to the what it should be actually. Okay, like that. Then interestingly, from -4 to 0, it's the same because it is already positive. You don't have to change it. Okay, if it is 0 or higher, you don't have to change, make it negative. Take the negative of it. And from there again, if you continue, it will be like that. Okay, let me, sorry. Okay, so I'm trying to make sure that I'm hitting the right marks, but somehow I'm missing that. So let me instead do this. Let me take some actual markers and do it. Okay, so it should go up like that. There, there, there. Why is it becoming so hard to do? Oh, okay. That's because my second point I did not choose correctly. Here it's 1 point something. So I should go there, from here to there, to here, to that almost looks like a straight line. What's going on? Okay, so I right now I give up on that. You get the idea, more or less. Okay, all right. Basically, the reflection of that shape. Okay, all right. Let us look at the domain and range. If you look at the original function from end to end, this is in the original function. This point is 2 comma -3, and one another crucial point would be here. So let me write its coordinate -2 comma 1. Okay. Now in the original graph, if you see, the domain is from -6 to 2, right? That's the x value. The range is the y value. Please write that and check with me, right? Now see what is happening to the new graph. the domain remains the same because taking absolute value only reflects on the x-axis, reflects only. So it doesn't it doesn't stretch or shrink horizontally, but the range is affected now because you don't have negative outputs. So the minimum is 0, maximum is the same. No, not the same. The minimum for the original graph was -3, so the opposite of that, 3 is the maximum. Okay. All right. So one more for you to practice. Draw the absolute value, then write the domain and range. Okay. I'm also going to do now. Pause the video and then verify your answer with me. And you should have noticed this. This whole part remains the same because the output is already positive. What's the only value that changes? From here to here. That from 1 to 2 on that interval, it's negative, so you make it positive. Okay. Now in the original graph, the domain and range, you go from -3 to 2, and range, if you look at the values, this is 2 minus 2, and the highest point here is 0, 2. Okay. So the lowest is -2, highest is 2. In the absolute value, the domain is same. Copy it. The range minimum starts at 0. The maximum is the opposite of the minimum. The opposite of -2 is 2. Okay? All right. Now that was a graph given to you and you just had to draw the absolute value. Now let's step up. There is an equation given. You draw its graph and then write the domain and range. You sketch the given graph, sketch its absolute value, and then determine the domain and range. Okay. If you feel confident, go ahead and do and then check. Otherwise, follow me here. This is the graph whose parent. Now there are two layers. Okay. This itself, the f of x itself, is modified from one basic graph, parent, or I would say basic parent graph. The basic parent graph here is the absolute value of x, right? And then that absolute value, I'm not going to write there because we have written it so many times earlier and we have enough experience. Okay. That absolute value, the basic graph has been shifted horizontally, shifted vertically, and also has been reflected because of the minus sign at the front here. That's reflection on x-axis. Okay. So let us do that. The absolute value +2 here. So left shift 2 units would have, and I'm just going to mark the vertex of it. Okay. And there is no stretching or shrinking. So if once you determine the vertex and the direction, you can draw the graph. Okay. The pink, the violet dot that you see here, that's not the final position. I'm just doing one by one. Okay. Starting from here, the parent graph is at origin, shift it left 2 units, then shift it down 2 units because of the second -2 here. Okay. And then reflect it. So the graph now should be facing down. Okay. So let me erase these two. That will be the vertex, left 2, down 2, and reflected. So you can imagine where the graph is going to be. Like that, I'll just continue here. Okay. All right. And then sketch the given function, that is the given function f of x. Now sketch its absolute value. And luckily for us, this whole graph is negative, so its entire absolute value is going to be on the other side. That will be the reflection, right? Okay. And only thing the absolute value achieved here is, not only thing, it achieved two things actually. First, it re-reflected it. So you're back to your original direction. So that minus sign will go away at the front, this minus will go away. And also, um, instead of 2 units down, now it is 2 units up, the vertical translation. Okay. So the equation would be, I'm going to write that now. Where do I write it? Let me write in a place where it's less jumbled. Okay, I'll use black color, sorry, red color, so I can write here. Hopefully you can see it. F of x, the equation will be the absolute value of f of x. Okay, will be the absolute value function which has been shifted 2 units to the left. That did not change. It's no longer reflected, so no minus sign, and shifted 2 units up. So plus 2. Okay. And one quick thing I will say here, before we go to the next one is, actually you can also determine this algebraically. Okay, if I were to look at the original f of x, minus of x plus 2 minus 2, I noticed that this whole thing is entirely negative, right? This absolute value makes it non-negative, and then you put a minus sign in front of it, so the first part is negative, and minus 2 is also negative. Both are negative numbers, right? Their absolute values would be the corresponding positive numbers and add it up. Think about that. But we did it graphically, which is the goal here. But you can also appreciate the same idea if you look at it analytically. Okay. Oh, the story of domain and range. Okay. Go ahead and do it. Okay. Now, in this case, when you say, the domain and range, um, the largest possible, I mean, the equation only is given here. Okay. So you have to think of the largest possible, the natural domain and the natural range. Okay. So for the original function, if you look at it, that's the purple one. Purple violet, sorry. It's more violet here. I keep confusing myself. Okay, in the violet one, you see, what do I see? Its domain is, of course, going to be minus infinity to infinity because nothing is stopping, from horizontally expanding. But the range is more towards negative and stops at minus 2. Okay. Then you look up to the absolute value and you see, so the domain is same, but the range now is the positive values. So starting at 2 to infinity. Okay, let me zoom out and show the whole thing, right? The domain and range. Okay. Piecewise function. Sketch its graph. You can sketch the graph if you want by plugging in different values of x and getting the values of y and then just joining the dots. Okay, remember, always remember that that method is always available. You can plot, the values of x, randomly create randomly choose the values of x and create a table and create a corresponding values of f of x, which will be the y coordinates. And if you get a bunch of points like that, xy, you can plot them on the graph and then join them by freehand. All right. You can, if you want to do that, but I'll leave that to you for maybe, you can practice that. Here I'm going to talk about sketching the graph by doing the shifts and the reflections and all the operations we have been talking about. Okay. So the parent graph for the first part here, the parent is y equals, x square, that squaring graph, right? But it has been shifted 3 units left and 4 units down. So 3 left, 4 down. It's here, the parabola opening upwards. Okay. For x equal or less than -3. So only for the -3 part. And because that's exactly where the vertex is, by the way. Okay. Now this time I'm going to draw the original also. So you'll have a better idea of exactly what shape we are drawing. This is the parent graph. Okay, for the first part, for the first piece there, but it has been shifted left. So this tip here has become this tip. The vertex has become this vertex here. So the part that gets copied, because we are saying x is equal or less than 3, is only this part. Okay. So 1 unit left, 1 unit up, 2 units left, you go 4 units up. So you should reach here. And then it will continue like that. So that's the part on the left. More freehand like that. Okay. Then between -3 and 3, it is 4 over 3x. So the line with the slope 4 over 3, just x, so which means +0. So the y-intercept is 0. It passes through the origin, right? That is one of the special topics we studied earlier. So that is kind of makes it easier to draw. Because from -3 to 3 until you reach the x coordinate 3, you are simply going to sketch the line. Okay, so the slope is 4 over 3. So if you go 3 units horizontally, you should go 4 units vertically here. And at this time, I'm going to erase the things that we don't need. Those are the parent graphs of different components. Okay, so the straight line from -3 to 3. And then actually on the blue line, you can kind of put a hole there if you want, but doesn't matter because they meet at that point. Okay, so the whole function as such does not have a hole because their values coincide at that endpoint. Okay, and from 3 onwards, it is exactly -4. Hole here because 3 less than x. Okay, till 5. Sorry, not continuing. Here also hole. Okay, between 3 and 5, the value is -4. All right. Okay. Let me erase this as well. So that's your graph. Sketch its absolute value. Okay. I'm going to do that in the purple color. This part is already positive. No need to do anything. Here -3, 4 will go to minus 3 plus 4, like that. This part that is negative here will become positive. Here is already positive, no need to do anything. And that minus 3, 4, but sorry, then from there, this minus 4 until it becomes plus 4 from 3 to 5. Okay? So the new graph now is continuous even at this point because they coincide now. The previous graph had a jump discontinuity there. Now it is continuous. Okay. So that's one takeaway here. When you do this absolute value operations, that is the only one probably where a continuous graph may become discontinuous, a discontinuous graph may become continuous. Okay, it can change. All right, let's write the domain and range. In the original, now let me use the same color. The blue one here is the original graph. Okay, you can see you go from here, including minus 3, not including 5. Okay, so minus 3 to 5, parenthesis, not including, and the range, you could see you reached this minus 4 here. Okay, actually reached it. So that's the lowest value, and the highest value is 4, which you actually reached. Oh, x less than minus 3. My bad. I'm sorry. It says x less than minus 3. It doesn't say what's the leftmost end. So from minus infinity to 5 is what you would say the domain is. Okay. The highest x value is 5, but the lowest is not minus 3. When you say x less than minus 3, on the other side is infinity, right? By default. So the lowest is minus infinity. Okay, you can see that graph continuing here, right? It goes to negative infinity on the left side. So the range also actually I should say, not 4 here, from minus 4 to infinity. Okay. And when you reflect it and obtain the absolute value, the domain does not change, right? But the range now, the lowest is only 0. So 0 to infinity. Okay. All right. So with that, I'm going to stop this video. In the next video, we'll talk about solving some equations analytically and then draw the graph to support that, we say. Okay. I'll see you in the next video.